All right. Happy Tuesday again. So I was just playing around. I just got info on this database. This is like a company database, and they've got some other really cool things that you can do from our librarian. But you can go like search by location and things and some other fields. So like if we look up computer programming, they don't have data science specifically, which is a little bit of a bummer. But they've got like some like industry breakdowns. Depends on how you want to do this here. Like data processing might be kind of close. It's hard to really tell exactly what we're looking for here, but somewhere in here we can like build out a search and say, hey, what companies are there in Michigan? Wow, is that my HDMI cord? That's crazy. So the projector's freaking out here. Okay, I think it's better now. I don't know what I did. But like you can put some stuff in, you can even look for specific technologies, which is really fun. So this one here had, where was it? Lord, it's like a ton of things you can search by, but like, hey, I want to look for Python. I don't know why that's a specific thing, but sure. So this is companies in Michigan that they think use Python, right, in those particular fields. It's super cool. So just for your own, if curious, like if you want to go look up companies that use Python in the area, this is a cool way to do it. And you can even like search by city too, which is kind of fun. So lots of cool opportunities. That's the D&B Hoovers database through our library, which is fun. I think she said this one's behind the VPN. So if you're not on the M wireless, you've got to use the VPN, which is just a small pain. It's not the worst thing in the world, or if you're on campus, it should just work out pretty well. So some cool, interesting things here. And then like they'll tell you about the company. So I just thought that was interesting. So thought I'd share that one. All right, back to what we're doing. Oh, I took a look at the labs for Lab 0 to make sure I could get to all your repositories. I think one person had a public repository. I left a comment and said, please don't make this public. And then one person didn't invite me, or I didn't get the invite, or I didn't click it and it expired or something. So just look for your comments on that if you didn't get a score, to know if we needed anything. Right? The Unix lab was just upload the document, and then Lab 2 we're getting back to the GitHub links here as well, so we should be pretty good for that. Yeah. All right, so this week we're moving on to new stuff here. We're going to look at recursion, so kind of take a deep dive into recursion. We don't really worry too much about Chapter 3 until next week. We'll do like a really quick overview on Chapter 3. It's very technical. Love technical terms. That's the more sciencey side of things. In general, we look at the complexity of algorithms is our technical term for that. It's how fast it runs, like how much time it takes for this thing to run, or how much space it takes for it to run, like how much do you need to have in memory. And generally what we look at is everything is in terms of the n size of items we're working on. So everything's based on, if you have a list of 10 things, it's going to be really quick because you just have 10 things. If you have a list of 1,000,000 things and you have to look at every 1,000,000 items here, it's going to be a little bit slow. If you have to look at every 1,000,000 items, and for every item you have to look at all 1,000,000 items again, and you're like n squared, that's going to be really slow with 1,000,000 things. So we use that measure to say how fast things are in terms of performance and how good they do in terms of memory storage. And then when we look at different ways of storing things, we look at stacks and queues and decks and linked lists and trees and maps and hash tables and search trees. We'll look at trade-offs for, okay, this one takes up more memory, but it's faster at this. Or this one is faster at this, but it's slower at this. So these different data structures have things that they're good at, have things that they're not good at. So we're just kind of expanding our toolkit for here's something that could be a good fit for solving our problem. And we know it's fast for reasons. And then I forgot to post quizzes for last week here. I just need to go like export and import the quizzes. So I'll probably remember to do that today. Again, they're going to be due every week. The idea is after we cover the content, we do our lab, you can finish the quiz on it. It's okay. If you need a little bit of extra time, it's fine, but don't leave 10 quizzes for the last week of class. It's not going to be helpful for you. So they've got due dates just to try and keep you on track with the content. I'm going to try and keep up to date on these things. Not all of them build on each other, kind of like we saw last time. So like stacks and queues and decks can be independent of linked lists, but we can also use linked lists for doing them, but they have nothing to do with trees. So it's not necessarily building on each other. It's okay if you get behind on a week for one of these things, but we should be okay there. We need trees for priority queues. So search trees need trees. So some of it needs some of the earlier content, but it's not the end of the world here. All right, so let's talk more about recursion here. Let me fire up PyCharm and start a new project. So we did some real basic recursion before, right? Did we do Fibonacci before? Okay, awesome. So this is week 3, recursion, and then I gotta put it in the right folder here. All right. Excuse me. Did I show you my new favorite mug? I got this over Christmas. I survived another meeting that could have been an email. I take this to my meetings to be passive aggressive. Just, it entertains me. All right. That little prompt, if your antivirus likes to scan these files, they just go a little bit slower. So PyCharm's like, hey, do you want to exclude this from antivirus? It'll make it ever so slightly faster if you say yes. So that pop-up happens every now and then. All right, so the real basic recursion, right? We'll do Fibonacci again because this one's pretty easy. So this is fib because I don't know how to spell Fibonacci for a given nth here. No Python interpreter. What? Use. Sure. Right, PyCharm got real confused, but I think it's okay now. Right? So Fibonacci said, hey, if nth is 0 or nth is 1, so really maybe we just say like less than or equal to 1, you return a 1. Right? We know the first two values of Fibonacci. You got to be 1. Everything other than that, we're going to return fib of nth minus 1 plus fib of nth minus 2. Right? That's the mathematical definition, the sum of the previous two terms. Right? We know the first two. Everything other than that, I got to count. Right? So then we can say, for number in range, 100 was too much, right? I think 50 started to get nice and slow. Print fib of number. Right? We give this a run and we see it goes decently. Oh, let me do the number here. So we'll print this as a formatted string. Number colon. That way you can see which one it is without having to count here. All right, there we go. So we get the first 30 pretty quick here. 34, 35, 36. It's not too bad. So we were at like 224 million, right? 39 million or so. You can count up decently quick here. But it starts to get very slow, very quickly. And this is where we start looking at that idea of complexity, right? Why is this slow? Well, because to calculate Fibonacci of 39, I'm literally doing 100 million function calls. Because the only time I ever get back a number is when it's 1. So fib of 39 is fib of 38 plus fib of 37 plus fib of 36 plus fib of 35 plus 34 plus 33, on and on and on. And then, oh, by the way, when you called fib of 38, that's 37 plus 36 plus 35 plus 34 plus 30. And that one is 37 plus 36 plus 35, on and on and on. So we get this like crazy, what's it, factorial, I feel like, growth in how many function calls this takes. So this is ridiculously bad here for recursion, to use this simple definition. This is just terrible. So we'll call this bad fib. Bad fib. And bad fib. I should have used my rename tool. That was bad. All right, so we got bad fib. So a better way of doing it here, right, doesn't even need recursion, right? We can define an iterative fib, takes an nth, and we have the current nth equals 0, and while my current nth does not equal the nth that I want, let's go and figure this out, right? So we have a current equals 0, starts at 1, right? Current is 1, right, for the first number, and then next is 1, current and previous. So previous number was 0, current one is 1 here. While my current nth is not the nth, we're going to need to go find the next one here, right? So then my next will equal the current plus the previous. My current will equal the that needs previous. Previous equals the current, and then my current equals the next one. Is that right? That's probably pretty close here, because we're moving and then current nth plus 1. So calculate the next value, save the previous value, move current, right? And then when we're done, we just return current. So this one should be a lot faster because it's just a loop now of counting upwards instead of counting 1 plus 1 plus 1 plus 1 plus 1 a bunch of different times here. I think that will work. Let's try it. So let's try iterative fib and see if that gives us some numbers here. And look at that, we got to 50 like right away. Turns out we can add up pretty quickly here. 1, 1, 2, 3, 5, 8, 13, 21. Yeah, I think we're calculating correctly. Sure. So we can do that one, right? So this is just a loop here. So we don't need recursion to do it. So a basic level of recursion is just a loop. We're just calling ourselves. So some problems can be solved with recursion, but not all problems can be solved with recursion, right? They have to fit a certain pattern here. So when we look at recursion, there's really two things we're looking for, right? The first thing we're looking for is a base case, right? The simple solution. If I can reach a base case, I know what the solution is. I'm done for that problem, whatever the problem happens to be. And we'll look at a couple different things. We'll do a maze solver, we'll do a queen's puzzle, we'll do a knight's tour. We've got a couple fun ones we can do. So the base case is the simple solution, problem's done, right? The next thing you have to be able to do is break down a complex problem. Approach the base case, right? So if I don't have the base case, can I make the complex case simpler? Can I get one step closer to the base case where I know what the solution is? In our case, sure, just -1, right? So this fits the requirements to be solved recursively. Doesn't mean it's good for it. It's actually slower to use recursion than it is to use just a simple loop here, but sometimes this stuff is hard. Did we look at the Towers of Hanoi last semester? Little stacking disks? Someone said maybe a couple head nods. So that one's really fun here. I think we looked at the code for it. Tower of Hanoi. 3D. So you can do it real fast here. I don't want to play, I just want to see it. Here we go. Here's the little visualization. So you can't put a bigger disk on top of a smaller disk. So the hard problem is moving 3 disks. Well, the easier problem is moving 2 disks. Well, it's hard to move 2 disks. How about moving 1 disk? Okay, we'll move 1 disk, then we'll move the 2. Right? I just want the illustration. I don't want to play it. I guess we can play it. Math is fun. Tower of Hanoi. Let's do like 4 disks. Okay. So the hard problem is solving 4 disks. How do we move 4 disks from here to here? Well, I can't do 4, so let's do 3 from here to here, then move the 4th one from here to here, and move 3 from here to here. Right? That's how we can move 4. Well, I can't move 3 yet. How about we move 2? All right, so move 2 to here, move the 3rd one here, and then move the 2 from here back to here. Oh, well, 2 is hard. I can't move 2. How do I move 2? Oh, well, let's move the first one out of the way. Grab the first one, put it, oh, I forgot where we were going, over here, over here, over here, over here, and then we repeat. Well, moving 2 is hard. Well, let's just move 1. Okay, let's move 1 over here, move 2 over here, move 1 here, and then we're back to, okay, now we have the 4th disk, right? Move the 4th disk over here. Now I can move the 3 again. I want to go from here to here, but I can't move 3, so I have to move 2. I can't move 2, let's move 1. So move 1 over, the second one over, put that one back on top, move the 3rd one over, and then repeat. Now let's move 2 from here to here. Well, I can't move 2, so I can move 1, and then move the 2nd, and move the 1st one. Well done. The computer's impressed with me. You guys impressed? A little bit? Okay. All right. That would have been bad if I couldn't do it. But this is super easy in Python with recursion. Geeks for geeks. Here we go. Like 4 lines of code here. Right? If the n is 1, do it, and you're done. That's the base case. We found a base case. If you want to move 1 disk, sure, move it. Easy. If it's not, okay, we'll move n minus 1, and we just flip the holding peg. Right? If you want to move from here to there, the middle one is the extra peg. Let's do 3 from here to here, and leaving that one as the extra, so we can move the 4th one. Right? Then we just move the 4th disk, or the nth disk, to that location, and then we repeat, moving those n minus 1 back off the holding disk, back on top where we wanted it to go. That's all it is. So doing this without recursion is much harder. Iterative. Look at this nonsense here. So here's the iterative algorithm. Gross. Where's the actual code for it? Here we go. So to do that, we have to have a stack here, or adding stuff onto. Let's do it in Python. Come on. There we go. So we have to have this stack. We have to push items on the stack. We have to move disks. We have to pop items off the stack here. We have to push things and move things. Like, this is gross. So some problems can be solved easily with recursion because it's a natural fit. That's why we like recursion. So if we think about things like your file system, when we make folders inside of our GitHub directory, we're making folders, and you can put folders inside of folders, and we did that for the Unix lab. You put a folder inside your folder, and we move things around. Right? In code, if we wanted to go find all of the files here, we have no way of knowing how many folders you have. So I don't have a simple loop like, oh, hey, while folder number is less than 10, go open up a folder, go open up a folder, go open up, because you could have 50 folders if you're crazy. Right? Hey, here's my school folder, here's my winter semester folder, here's my class folder, here's my assignments folder, here's my code example. Like, you can go as deep as you want here with folders. Nobody cares, right? Go nuts. So recursion says, if it's a folder, go into it. If it's a folder, go into it. If it's a folder, go into it. Eventually, we'll get to where it's not a folder. We've reached the base case. You're not a folder, recursion's done. Now I can say, here's your file, I found it. So some problems work very well with recursion because it's just a natural, just keep on going, keep on going, keep on going. Eventually we'll hit that base case. At some point you got tired of making folders, right? And we're going to find your main py file or something and run that. So we've got some good things with that. Now, base case, complex case. So what we can do then, this one was kind of boring here, but that's fine. We're going to make a maze solver. This is one of my favorite things to do here. So I'm going to add a new module. We'll call this maze solver. And we'll call this a class. So this will be our class for the maze solver here. And to create a maze solver, you need to give it a maze to solve, right? Here's the maze to solve. So our self.maze will equal the maze. Great. And then a couple things we want to use here. So we can have a couple other values. If it's not a self.value, it's a class level or a static value. I don't think we spent a lot of time on these, but I can say, hey, open is a space. Blocked is, how about an X? Oops, there we go. And so when you're designing a maze, you're going to give me the open space or a blocked space, right? This is just nice because I have a name for something here for me to use. And then we want a start is an S and an end is an E here. Again, we can use whatever characters we want here, but what we can do now is we can design a little maze. And I can say, hey, you know, here's a space, here's a wall, here's a space, here's a wall, here's a space. Or maybe we'll make the start here. There's a space, there's a space, there's a space, there's a space. Space. Maybe I have a wall here, and over here I have some more walls. Right? So you can see there's kind of a path going through our maze. And then we'll have, this can be, maybe we'll put a wall here and make that the ending character. And then we have some walls over this way or something here. I don't know. It can look like whatever we want here. So we can make this little text-based maze. We can make our maze solver go and solve it here. So something like this ought to work, right? So we know we go down, 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 over. So we can see this pretty easily in our heads, how to solve this problem here. Actually, let me take this one out here. Let's have more than one solution. No, we'll do one solution to start. We'll come back and edit that. So to represent our maze, we probably want some sort of two-dimensional list, right? A list of lists is going to be easiest here for us to use text here. So back to our main. So we'll say, hey, our maze is a list here of lists, right? And then the first list will have all this nonsense in it here. So we'll have S and a wall. And what was that? Oh, I can't even remember now. A wall, a blank, and then another wall, and then a blank here. Right? That's our first row, essentially. And then I think our next one was just all open, right? So we just want it to be open. And then our third row was going to be almost all blanks here. And then our fourth row was going to be the end here, and these ones were open. And then the last row, what did we have for the last row? We had just the two walls over here. And that was open, right? I think that's probably pretty close. And then that row ends and that, okay. Something like that. Right, so whatever representation we want that to look like here. Maybe pull that back in one. Oops. Nope. Grab a couple. Okay, does that make sense? So we've got starting characters, we've got ending characters, we've got our maze here. We can go and navigate. Now we see the solution pretty easy in English, or just in our heads, because we're smart people. We're better than AI, of course. Then our maze solver says, okay, give me the maze, and now I need to go solve it. Right? So to solve the maze, it has to go figure out what am I going to do step by step by step by step. Right? So the maze probably needs to know, current row index is something, and a self.current column index is a something. Self. There we go. Self. Right? So I know what row and column I'm at. Because what we can do is move around our two-dimensional list by row and column. Okay, now I'm at row index 1, row index 2, row index 3, whatever it happens to be here. So we need to go find the start then. So for row in self maze, if my start, so this is self.start is in the row. I know I found it here. Then my self.current row index should equal row dot. What is it? I want the location, right? When I have find self.start, doesn't find give me the index here? Why is it? It doesn't know it's a list is the problem here. I think isn't it find? Goodness, I don't remember right now. Maze.find? No? Oh, index. There we go. On index. Row.index of the start will be my row index, right? Now, that's actually not the row index. Shoot, that is going to be the column index, right? Where it is in the particular row is the column index. Oh, this is getting annoying now because now I have to count my rows here. All right, this one's a little bit annoying here. Let's change it up here. We'll say for row index in range, length of self.maze, right? And for column index, in range, length of self.maze at the row index, right? How long is that particular row here? If self.maze at the row index at the column index is equal to self.start, then my self.row index and column index can match, right? Equals the row index and the column index. So we just want to find the start character, right? So we'll go look through for every index in row, for every index in column, go look at it, see if it's a start character. This is probably easier than using find. I don't know, because we had to count the rows anyway. This is probably fine. Does that make sense? Just go look at all of them. Okay, so go find it. So now we know where to start, right? Okay, we're getting closer now. So I have my starting location. Now we want a way to solve our maze. So we're going to define a solve, right? Remember, we had to have two things. We had to have a base case and a complex case. Well, what's the base case? How do you know if you've solved the maze?
If you reach the end.
Yeah, so if my self.maze at the self.current row index at the self.current column index is equal to self.end. If we reach the end, print solved. Done. Solved. Right? That's our complex case. That's our base case. We're done. Cool. What do we do if we're not there? We'll have to try something. Right? How do we get one step closer to the base case? Well, you have to go up, down, left, or right. Right? Okay, so we're going to try it. So if it's not solved, else here, let's try and solve it. Excuse me. So what do you want to do first? Up, down, left, or right? Really doesn't matter what order we go in. We just have to try it.
Down.
Down, okay. So we're going to try down first. So we need to see, can we go down here? Right? So is that space open? So we'll say, okay, if my self.maze at the self.current row index -1, right, to go down a row, I'm sorry, +1, right? Because 0 is at the top left, we don't have an origin because we're not math. So 0 plus a row is going down, plus a row is going down, plus a row is going down here, right? And then at the self.current column index. But really, is this even in bounds first? We have to check, right? Is that a valid index first? So we got a couple things we have to check here then, right? So if self.current row index plus 1 is less than the length of self.maze, right? Is there a row at that index? So if we're at row 5 and you try and check row 6, there is no row 6, it's going to crash on us. That's an invalid index. So if that's true, and that one here then is self.open, right? Is the space below me open? Right? Does that mean I can go down? If it's within the range of the maze and it's open, can I go down? Yeah, okay, so let's go down. Okay, so if I can go down, let's go for it. So let's move then. We'll say, hey, self.current row index plus equals 1. Great, we moved. Right, now what do? Now we recurse. All right, we moved, call it again, so self.solve. Awesome. Right, now I don't want these to be else ifs, because I want each of these to happen no matter what happened before. Because if it's else if, we're saying if you can go down, don't do anything else ever, which is not what we want. Because if you can go down, great, but eventually maybe we have to try right, or maybe we have to try left, or maybe we have to try up. So each of these is just going to be another if here. Now, I'm feeling particularly lazy here, efficient here, and I don't want to have to copy paste this and change a couple things, right? So wouldn't it be nice if we had a little helper function here, like can move to, right? And maybe we say the, target row index and the target column index, right? So can I go to this space here? It's the same idea, but I need to check, is it within bounds and is it open? Right? So remember when you're doing these things, you can say, hey, if we want 0 is less than or equal to the target row index is less than the length of self.maze, right? And 0 is less than or equal to the target column index is less than the length of self.maze at the row index. Return true. True. There we go. Remember, don't do this if return true, else return false. Just return the whole sucker, right? Because it's already true or false, right? So we can just say, hey, return this and this. But then we also had to check, was it open, right? So, and self.maze at the target row index at the target column index is equal to self.open, right? Is the row within bounds and the column within bounds, and is it open? So now I have my little can move to, and I use my underscore to say, hey, this is a private function. No one else needs to bother with this. It's just a helper function for me to use, and I don't have to write the same code twice. So now I don't have to do it this way, this whole big long thing here, right? I'm going to say, hey, if I can move to self.current row index plus 1, self.current column index. And that's self.can move to, right? Okay, if I can move to that location, great. So this one was down, right? Row plus 1, cool. So we tried down. How about the next one? We want to shoot this one here. We did down. What should we do after down? Right. Okay, so right then is going to be column plus 1. Column index plus 1. Take our column index plus 1. Okay, we'll try right. We tried right. What else? Left, sure. All right, so left is minus a column, right? Minus a column. And that leaves us then, we did down, right, and left. All we got left is up. Thank you, yeah. Some people are awake, I know, it's tough, it's tough. It's been a day. We'll take the row minus 1 and leave the column alone. Okay, there's up. Great, we call solve. Okay, so our complex case then is we didn't solve it, we didn't reach the end, so let's try moving. Go to another position here. right? Getting closer here. And then another fun thing we can do with this maze then is we can make this printable here. Define a string, right? So how do I represent myself as a string? Lots of ways to go about it here, right? I like the string join. Again, the book likes string join. I think it's a little bit fun sometimes. It's kind of obnoxious to have to read it, but it should work out pretty well. So we're going to take the /n character and join that. So use that character to join. For row, we want row for row in self maze. And we want the string representation of that row here. So we're going to get, it looks like a list, which is fine. Just turn it into a string, put a bunch of new lines together. Right? So we'll get the first row, a new line, second row, a new line, third row, a new line. This way, we don't have to trim off that last trailing new line, which is nice. It's not the hardest thing in the world to do, but this is not too terrible here to represent a maze as a string, right? Okay, so we're getting closer here. But what's going to happen, like if we just think through it here and we give it this maze, right? We're going to start here and say, okay, can we go down? Yes. Okay, so we go down. We're here. Can we go down? No. Can we go right? Yeah, we can go right. Okay, so we go here. Great, now we're here. Can we go down? No. Can we go right? Sure. Okay, we go right. Can we go down? Sure. Okay, we go down. Can we go down? Sure, we go down. Can we go down? Sure. Can we go down? No. Can we go right? Sure. We go right. Can we go down? No, it's out of bounds. Can we go right? Sure. We go right. Can we go down? No. Can we go right? Can we go left? Oh, I can go left. I'm going to go back here. Oh, from here, can I go down? No. Can I go right? Sure, go here. Oh, go left, go right, go left, go right. So we need a way to make sure we don't step on ourselves, right? And go back onto a step we were before. Remember Hansel and Gretel? Leave little breadcrumbs or rocks so the birds don't eat their poor pieces of bread and they get lost in the woods. That's such a weird story to tell kids, by the way. Like, it terrified my kids of going out into the woods. Like, we're going to get lost in the woods. Like, no, like, okay, poor kids. Just some weird cautionary tales for children. So what we need to do is mark that we've been somewhere so we don't step on it again. So as we're going here, we need to go and put a little marker, like a little, you know, we say, hey, we've visited is a pretty common term for this. We'll say visited is, maybe we just add like a period, just a dot here to say, hey, I've been to this space. So before we go and recurse here then, I want to mark my spot as visited. We'll say self.maze at the current row index, self.current row index. And really, I'm going to do the same line of code a bunch here. So I'm going to save myself some trouble and add a little helper function here. Define mark visited. Visited. So self.maze at the self.current row index at the self.current column index equals self.visited. Nope. Self.visited. There we go. Uppercase. All right, go put the mark there. Right? So I can mark myself as visited. And really, I'm going to do it every single time here, right? So I could just do it first. Now the problem is it's going to erase my start mark and my end mark. That one's a little bit sad. So we could have it 4 times here, or we could add a little check at the top. I kind of like the check at the top, so we can say, hey, if self, or maybe we just add that to visited here, right? So not only do we check these things here, so if self.maze at the current row, self.current row index, current row index at the self.current column index does not equal self.start, and it doesn't equal, copy that one, doesn't equal an end, then we go mark it as visited. Shoot, I need that backslash. There we go. So if it's not the start and it's not the end, it should probably be tabbed in one more. This gets a little long here. This is why some people like shorter names. Most people aren't zoomed in this far when they code, because they can use like a decent, you know, goodness. Like, you can still read, I can read this font pretty easily. It's just harder to read up on the screen, right? So like this would fit on one page here, but I'm zoomed in kind of just to make it more visible. Is that okay? I know it looks a little ugly and I feel a little bad about it here. All right, so we'll mark it as visited as long as it's not the start and end, right? We'll mark that as visited. So now, right, we'll add our little breadcrumb. We'll say, okay, sure. Hey, I stepped here. Okay, I stepped here. Okay, on and on and on, right? And eventually we'll get to, okay, I can't go left here. How about up? Oh, hey, let's go up, and I got to the end, right? So what we want to do then is at the start of every time we're going to solve, we'll just print self. Say, hey, what does the maze look like? Just print it out. Again, I don't usually use prints in classes. That's kind of a bad habit to be into, but this is just let's kind of like see what's happening with the debugging. Yeah.
So basically, once it visits like an entry, it just marks the dot.
Yeah.
If it goes back to it and realizes it is dotted, it goes to another place.
Yeah, it says don't go back onto a dot. So don't go left, right, left, right, left, right, left, right, or left, right. Right? This way we don't crash. Yep. We would get into an infinite loop. I guess I should have left that here so we would have seen the Stack Overflow, which is fun. But that's okay. We can get to that in a minute. So we make sure we mark it here. Oh, I didn't actually call the mark code. So we got to print it. So let's mark it first, right? So we'll do self dot mark visited, and then we'll print, and then we'll see, did we get to the end? And then if not, down, right, left, up, right? So let's see if it works for us here. So let's go back to our maze solver, maze equals maze. We got to import it here. Shoot. Okay, hang on. So import from maze solver, import maze solver, a maze solver given the maze. Oh, I probably can't use that twice. Maze solver, and then call maze solver dot solve. Let's go ahead and solve it. Give it the maze. Here's my maze here. Let's solve it. We print. Oh goodness. String return non-string type. We crashed. We were close here. Where did that happen? Print self. Self should have done the string thing. Why did it? Oh, I didn't return anything. I was supposed to hit return here. If we return the string, I built a string representation and didn't give it anywhere. There we go. So that was why it was a non-type here. Let's try that again. Hey, look at that. Now it's a little bit ugly though, because we've got all these like, they're all smushed together like. It'd be nice if we could actually see the individual steps. So maybe we print self and then we just print a blank line just to see. Hey, look at that. Okay. So our first maze here, right? We didn't mark the start as visited because it's an S. We don't want to erase that. Then we marked it and printed it. We went down. We marked it and printed it. We marked it and printed it. 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 But we never got to solved. We got to here, but then it just kind of stopped. Why didn't we ever get to solved? Well, we said, hey, if you can move to was open. Is the end character the open character? No, so we need a little more logic here. So you should be able to move on to the end character, right? So really, this one or this one. End, right? It's an end or open I should be able to walk onto, right? Why does it? I don't know why sometimes it needs a slash and other times it doesn't need a slash. Honestly, it confuses me sometimes. I don't know why. Well, now let's try it here. So let's go back to, we can run our maze solver. Hey, now we solved it. All right, so we found a solution. It's pretty good. But what happens now if we change this up here and I have this one being a space here? You run that one? What happened here? Well, we got to the end. Okay, let's see. Let's follow our little breadcrumb trail, right? We did the first one, did the second one, did the third one, did the fourth one, fifth, sixth, 7, 8. Got to the end, marked it as solved, and then we kept on going. We went up. That one looks the same here. Well, that's interesting. It should have just stopped, right? Well, something kept happening here, so marked as visited. Why did we get another one marked from here? That's really interesting. Where did that come from? Is one of these out of line here? It's the else case. Didn't happen till after that one, right? So we should have got to the end, we marked it as solved, and then we printed more. And then we said it was solved again. So somehow it went up and then down again. And one last, it went up. How did it go up from there? I'm confused. Hang on, so we found the end, printed it was solved, and we should have done something else. I don't know, let's pause here. I don't know, let's find out. So let's run that in debug mode. All right, we got to here, print solved. Let's step over. As we did up, we finished our solve call. Now we're gonna try write. Okay, so here was our maze, right? We did all these things. Now we are trying, right, in this call stack over here on the left, these are all the different function calls that happened, right? Each step of the way as we're moving. It has to remember as we're going. So now we finished going right, so that one should step out. Up. Where are we here now? What is the current row index? 4 and 3. 3 and 4. So when this stops running here, like when we get to the end of one of these function calls here, it just keeps on going from where it was, right? So we called up from this position here. When we were here, we called up, right? The next thing it had to do after checking up was, okay, that one finished. So that one was done. Then we got back to this function call here. Well, we did right, remember? So it left off here at right. And it said, okay, can I go left? And we never changed the current column index. We never put it back to what it was before here. So it couldn't go here, but it said, hey, you could go up because our current column index was still at 3, 4. Right? We were still at this position because we never undid our steps here. Right? And we would see, hey, if we changed our maze a little bit here, we said, hey, if I put an X here, and we give it a run, we never find a solution. It says, oh, well, I got stuck here and I stopped, and I gave up because I couldn't do anything else. So what we have to do is we have to undo that step. So if we got back from solve and we're not solved, we're going to undo our step. So we should just be able to undo this here and say, okay, hey, let's put this back to where it was here, +1, so you can keep on going from where you left off here. So we'll undo our step here, +1, undo the step here. That's a -1 then to undo, right? And then a -1 here to undo. So we tried solving it. Whatever happened, if we finished or not, now we need to undo it and go back so we can try it again here. So now when we run it here, now we'll find a solution. So it's going to try all of these things here and step back when it gets stuck. So this is called backtracking. Right? I tried this, let me take a step back, and then keep going from where I left off here. So first step, second step, let me zoom that in a little bit more, sorry. Third step, fourth step, fifth step, sixth step, we hit a dead end. So it says, okay, that didn't work. Let me come back to here. Well, I tried down, I tried up, I tried right, I tried down. Now I have left to try, so it tries left. Okay, cool, I tried left, tries left. That doesn't work, so it comes back to here, comes back to here, comes back to here. It says, okay, well, I tried down, now I'm gonna try right. And it goes to the right. It says, okay, I'm gonna try right. I'm gonna try down, I found the end, I'm solved. But then it still needs to keep undoing, right? It says, okay, I did that, but now let me come back. I tried down, how about up? No, that one didn't work. That one finished, we come back to this one and says, okay, let me try my next up here, right? So it tries every single possibility to find a solution here as we go. So that seems to work, right? It's finding a bunch of different solutions here as we go. Next thing now, if we change our maze and have 2 different solutions, is it gonna find both? It says, okay, hey, I solved it here, right, this direction, and I solved it here going this direction. So you see there were 2 possible paths, which is kind of cool, right? So this one was this path, and this one took the other path. Now it's hard to see the path though, because we didn't undo our steps. So we can also unmark, right? If we mark it as visited, we might also want to mark it as, or unmark it as visited, right? So when we mark it as visited, when we undo that, we want to undo that step, right? So after we've tried everything here, we'll take this mark visited, and how about I change this here? So let me refactor this. Let's rename it here to just mark. Right? So we can call mark with self.visited here. Once we're done with that step, then, right, I've tried all of these things here. I've tried up, I've tried down, I've tried left, I've tried right. Let's see, where is that line up here? Should be right about here. This should undo it here. We'll say mark it as open. Right? If we went through and marked it as visited, let's undo that and mark it as unvisited here. Right, mark it as open. Oh goodness. Self mark. Oh, I didn't add that variable here. Oops, sorry. The mark here. That's what the problem was. So we'll just call that the mark. This one here. Mark as the mark. All right, so now we can say, okay, mark with the visited mark, or take that visited mark back off, because I want to see what that path looks like. And now we'll see the two different paths, hopefully, here with a solution. Where did that one go? So here was a solved solution with this path, right? This one, 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 here. And then we'll see our other solution this way with this step, 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 this step. We found it. So we can see it was solved. So it might be nice then, so instead of printing every single time, right, maybe we only want to print when it's solved. Right? Maybe we can now print self here. So we only get the solutions here then. That one and that one. Oh, we don't need these extra prints then either. Oops, there we go. That'll make that a little cleaner here. Right? So here it's solved with this solution, and here it's solved with this solution. So we found both possible paths because we undid that step here. Right? The other thing we want to track is, well, how many steps was it? I can count them here, but I'm lazy, right? I want the computer to count for me. Yeah.
This thing, like, I'm going to be. I'm just curious. Now, is the concept different from, like, the concept of this recursive algorithm? Is it different from, like, the jigs? I don't know how to say the name, the jigstaw's algorithm. Now, the jigstaw's algorithm is about, like, finding the.
Yes, so backtracking recursion paths finding is terrible. This is a terribly slow algorithm because it literally tries every single possibility blindly. There are smarter algorithms that can do pathfinding, but this is a nice basic example of backtracking recursion, and we're going to use backtracking recursion for lots of things. We'll have a lot of examples of why we can use backtracking recursion, and it's simple-ish enough for us to think about, okay, I'm going to try this. If it doesn't work, come back. Try the next one. Right? So it gets us, this is a nice way of, oh, this probably could be recursive and quick. Not optimized, not fast, right? Because so if you give it a big maze, it's just going to go nuts. Because if you've got 1,000 different places you can go, it has to try all 1,000 different paths. Right? In our case, we had like 4 different paths. It wasn't too bad. So yeah, not a great maze solving algorithm, but just gets us into the headspace for recursion. Right? So if we want to count how many steps it took, that's something we need to be counting, right? So we'll start off with steps here, right? So we'll have like self dot number of steps starts at 0. Every time we call solve, we should add a step, right? So we'll take self dot number of steps plus 1. But remember, when we're done and we undo, we have to unstep, right? Or undo that. So self dot number of steps minus 1. So once we find a path here and we undo that, uncount that step. We went back to where you were, right? So we print then, here's solved in self.number of steps. So we run that, we see, okay, hey, this one was 10 steps, this one was 8 steps. Because we're marking something and then we're undoing it. We're marking it, we're undoing it. We're marking it, we're undoing it. Right? So we could see how many steps we have at every single point if we go back to print ourselves here. we could see how many steps it was as we go. But this way we can find, okay, this is how many steps it was, this way. All right. How much time do we have? We have a little bit of time. Oh, shoot. Thursday. I wanted to do more. Okay, let's do the next example because I'm not going to be able to be here Thursday. I have to follow up with the surgeon, and his office was like, well, he's busy in surgery these other days. Can you come Thursday afternoon? I was like, sure. Wasn't ideal, but yeah, I won't be able to be here because it's like a 3 o'clock appointment back by my house in Novi. It's like I could be here for 10 minutes maybe. That's not very exciting for anybody for 10 minutes before I have to leave. So let's not plan on coming Thursday here. So I'll do one more example with recursion, and then we'll do another recursive example in lab, and then our next project will be on recursion. So we'll do a lot of stuff with recursion, lots of recursion, lots of recursion, lots of recursion, following these kind of examples. Does that make sense? Okay, so the next one we want to do is one of my favorite puzzles here. So this is the 8 queens puzzle. Here, and there's a good Wikipedia page for it. Here we go. Thank you. So if you're not familiar with chess, that's okay. You should be, because chess is amazing. But a queen is a piece that can attack anything in its row, anything in its column, and anything in a diagonal in any direction. It's one of the strongest pieces in the game. So any diagonal here. What?
One of the strongest.
Oh, you can have more than one. And the king is strong, he just doesn't attack very well. I don't know. You're right. The strongest piece in the game. Is that more fair? Thank you. So, how do we place queens on the board here? In such a way that 8 queens can go on the board, that none of them are in the attacking path of any other queen. So, for this row here, there's only one queen, and there's no other queen in this column, and no other queen in its diagonals. Right? For this row, there's only one queen. There's no other queen in this column, no other queen in this diagonals. Right? So we need to figure out how do we do this? Well, let's think about it recursively. Right? What's the base case? How do I know if I'm done? I got 8 queens on the board. If I can put an 8th queen down, I'm done. Right? If I don't have 8 queens on the board, to make it simpler is I have to put a queen down. Let's put a queen on the board. Eventually, I'll probably get to 8. Right? And we're going to use that backtracking piece here that, hey, if I get stuck, just undo. Oh, okay, that didn't work. So what we end up doing here, let me just find a nice chessboard image here I can draw on. Okay, that'll probably do here. On snip tool. Where's my snip tool? Oh, because OBS puts it in like do not disturb mode. Shoot, snip tool. Hang on, we'll get it here. We'll get it. Rectangle, yes. New snip, thank you. Okay. There's our snip. So what we're going to do then is we're going to say, okay, the first step is to put a queen down. Queen. Oh, that's a little thick for a line there. That's okay. Let me erase that one here. Put our queen down. Done. Next row. Can we put a queen at column 0? No, because there's already a queen in that column. Can we put a queen at column 1? No, because there's a queen in the diagonal. Can we put a queen at column 2? Sure, that one's open. Recurse. Can we put a queen here? No. Queen here? No. Queen here? No. Queen here? No. Queen here? Sure, go for it. Put a queen in. Recurse. Queen here? No. Queen here? Sure, looks open. Put a queen here. Recurse. Queen here? No. 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 Here? Sure, why not? Let's put one in. Recurse. Queen here? No. 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 This one diagonal, no. This one diagonal, no. This one diagonal, no. We couldn't put a queen down. Okay, go back to where we were and undo. So this queen is no good. Undo that step. Keep on going from where we left off. How about here? No. Here? No. Here? No. Here? Sure, why not? Put a queen down. Recurse. Can we put a queen here? No. 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 Okay, well, no good. That was bad. So undo. That was no good. So if that one was no good, go back to here. This is no good. Here. Okay, that one's no good. Here, no. Here, no. Here, no. Here, no. Here. Sure, why not here? Try a queen here. And it will just literally try every single possibility here. Eventually, we'll find a solution. Right? Eventually, we'll find all 92 solutions. if we keep on running, right? There's only so many combinations here, which is nice. I think it's 92, right? Isn't it 92? Yeah, 92 solutions. That kind of piece of information should not be in your head. I happen to think this is a fun puzzle, so that one is in my head, right? So we can make a new Python file. We'll call this the nqueens, nqueens module here. And we'll write a class for nqueens. Now, this can be for almost any n. It doesn't work for all n's, but usually we start with 8 because that's the easy one here. But you don't have to, right? So that's why it's n queens. Usually it's 8, but so we'll have our init function here that could take an n if you wanted to make that size of your board. If you just want it to always be 8, that's okay too. That's fine. So we'll have a self.board then is my list of lists, right? And then for row in range 8, let's take self.board and we'll append a new list here of 8 spaces. 2, 3, 4, 5, 6, 7, 8. There we go. Append in another row with 8 spaces. We'll have an 8 by 8, right? There's probably a faster way to do that. I don't remember what it is. This is the first thing I came up with. That's okay, right? So we got an empty board. Then we need a self.number of queens, right? How many queens do we have on the board currently? Well, none right now, right? All right, and then we have a solve function. How do we know if we're done? What's our base case? We said we're done, right? We have 8 queens. So if self.number of queens is equal to 8, print self. And probably another print, right? So again, we're just going to steal the maze solver string representation here because I think it works the same way for us, right? Why not? So here's our string. Instead of maze, it's board now, right? Same idea, just new line separate. So it works out pretty well. So cool. If that's not the case, then, well, now I need to try something. So I can kind of cheat a little bit here because I know if we go row by row by row by row, that we'll start at row index 0 and then row index 1 and then row index 2 and row index 3, on and on and on, right? The current row I'm working on is always the number of queens that I have, right? So when I have 0 queens on the board, I'm working at row 0. When I have 1 queen on the board, I'm working at row 1. That's just a piece of information I know because we're going to tackle it row by row by row. If you went column by column by column, you just have to change it up a little bit, right? That's all. So I know I'm always working in the self number of queens row then. So for column index in range 8, and again, if you use n, you'd use n value instead of 8 every time here, right? We're just using 8 because we're starting with 8 here. So I'm going to see, can I place a queen? Right, so if self.canPlace queen, and that was probably a helper function, can place at the column index. Right, I know the row number is always my number of queens. So if I can place it at the column index, then I'll place it. Say self.board at the self.number of queens at the column index is equal to a q. Put a queen in. Or we should probably use like a nice, have a queen mark in here. Queen equals q, something like that, and open equals a space. Sure. This is a good habit to have these static values here, just so you don't have, we'll call them magic numbers, right? It's hard to typo the letter Q, but again, it's possible to typo things. So having these static values gives you like that checking. If I typo this, it won't even run. I'm going to get an error, so that's nice. So if I can place it, great, place it in, and then call self.number of queens plus 1, and then recurse, self.solve. If we come back from here, we have to undo. Well, what's the undo step? Well, take my queens away, right? Take the number of queen away, minus 1, and then put it back from queen to open. Open. Go to the next one. So really the tricky piece here now is, can I place it, right? Well, how do I figure out if I can place it? Okay, well, we can write that. So we'll add a little helper function for can place, given a column index. Now, we can cheat a little bit here as well, because if I'm going row by row by row by row, I know I never have to look down. I never have to look at beneath rows. I only ever have to look up, right, as I'm going. So what I need to do is check, is the column clear? Is my backwards diagonal clear? And my forwards diagonal clear? right? Those are the only ones I have to check because I know I'm only putting one at a row, and I know there's never anything underneath me, right? So really then that can place is the combination of return self dot is column open, given the column index, and self dot is backwards diagonal open. Now for the backwards diagonal, it'd be nice if we had the row and column to start with. And then I've got those variables and I can just follow them up backwards here. I've done it before, it just makes life easier. So I'm going to pass both those things with self dot number of queens and my column index. And I also need then is the forwards diagonal open. So let me actually just arrow this down one here, right? And then another and is forwards diagonal open, right? And I just, all three of those, if they're all true, if they're all open, I can place a queen there. If any one of them is false, the whole thing will be false because we're anding, and we stop, right? Cool. So again, we're doing our functional decomposition. We're taking a big problem, breaking it down. It's easy to check a column. It's harder to check all three, right? I can check one at a time. So then we'll have a self dot define is column open. Here, let's given a column index. Right? So now for here, I just have to say for row in range self.number of queens, right? Because I never have to look lower than that. I could look at all 8, but then we're wasting time, right? And no one wants to waste time here. So if the self.board at the row, that should be row index, right? Row index at the column index is equal to a queen, self.queen, I'm going to return false. I found a queen in your column, don't do it, right? And I'm going to look for every row 0, row 1, row 2, as far as we need to go, right? On the third queen, I'll check the first 3 rows, or the first 2 rows, right? And on and on and on. If we return false, we're done. If we didn't return false, I can return true, that column must be open, right? Same idea now for my diagonals here, but now instead of just going straight up, I need to go forwards up or backwards up, right? So for my define is forwards diagonal open, given a row index and a column index. We're going to check. So the backwards diagonal means up a row, minus a column, minus a row, minus a, or you're going that direction, right? Minus row, minus column, up towards that top corner, right? So starting with this row and column of where we are is going to be open. That's fine, but it's okay. We don't need to start at like -1. We could if you want to save one extra step. It's probably more hassle than it's worth here. So we're going to say while my row index is greater than 0 and my column index is greater than 0. Right? If either one of those goes less than 0, stop. They both have to be true to keep going, right? Because I'll go off the board otherwise, right? So as long as they're greater than 0, let's keep on going. So let's check. Hey, if my self.board at the row index, at the column index is equal to a self-queen, self.queen, return false. I found a queen, stop. That diagonal is not open. Otherwise, take my row index -1, and take the column index -1. Right? We could do this with a for loop and a range. I find that to be a little bit more obnoxious because then you have like 2 of them and it gets a little awkward. I just like the while loop here because I think it's more simple. If you like the for loops, go for it. Right? There's always more than one way to do it. But we're going to say, hey, just keep on -1 to row and column, go back a diagonal, back a diagonal, back a diagonal from wherever we are. So if we're over here, I'm sorry, like over here, back a diagonal, back a diagonal, back a diagonal, I'm off the board. I didn't return false, must be true, must be open, right? That one's fine, right? But then we also need to check the forwards diagonal here. So at some point like this square here, oh no, that one wasn't, eventually, right, we'll run to one where the forward diagonal is no good. Right, you have to check the forwards, yeah.
Is that where the like letters and numbers come into, can be used?
Like the names?
Like on a typical chessboard, it's like...
Yeah, A1.
Yeah, A1. Could we use that in programming or no?
If you wanted to, we could name the squares. That doesn't really add any value for us, unless you want to say, hey, the queens are at A1, A3, you could name those 8 positions if you want it that way. For us tracking it, it's just A through H instead of 1 through 8. I don't know if that gains us a whole lot of value. Yeah?
to calculate like the time complexity of navigating that position?
So for every position, we're trying every next one, right? So it's going to be some kind of exponential, right? So the bigger the board is, the more things it has to try, right? So it could have to try, what is it, for this one, then it's got 7 more, and for that one it has 6 more, and that one has 5. Probably factorial at some point. There's some fancy math you can do. I don't remember off the top of my head. But
Now, factorial is the most inefficient.
yeah, because the bigger it is, the more things you have to try, times the more things you have to try, times the more things you have to try. So I'm just going to copy paste this whole thing here for the diagonal, forwards diagonal. Now the only difference here, still want row greater than or equal to 0, but now I want column is less than or equal to, I'm sorry, less than 8, right? Less than my n here. And then column will go up 1 here as I go still up a row, but forwards a column, forwards a column, forwards a column, right? Minus the row, forwards a column, right? So that one ought to do it here. And let's see if we can solve our n queens. So we'll have n queens, oops, I gotta import, shoot. So from n queens, import n queens, n queens. Here, we didn't end up taking that as an argument, right? Yeah, just an it here. And then n queens dot solve, and we should get, what's the red line here? Why is it red? I don't know why it's red. We should get all 92 solutions here. It's going to be, oops, invalid syntax. Oh, my, I have too many ands here. There we go. There. Sometimes I put them at the start, sometimes I put them at the end. I don't remember why. Let's try that. Okay, it didn't solve. Why didn't it solve? Let's see. Solve. Self-solve. Number of queens. Can place in the column index. Number of queens. Shoot, we're so close. Let's see, we tried solving, didn't go. Put it here, we marked it as open, we undid it, cursed, print. Why isn't it going here? How far did we get? I guess we can print it at every step here. That's fine, right? You can print self every step as we're kind of debugging it here. Let's see how far we get. It only prints once. So our can place must be screwed up here. Can place, return, columns open, diagonals open, forwards diagonals open, column open. If it's a queen, false. Oh, I never returned true on this other one here. So when we're done, then we have to return true. There we go. And when we're done here, we have to return true. Return true. There we go. We never tried a step here because those never said true or false here. So print, we don't need to print those. Let's give that a run. Hey, there we go. So here's a bunch of solutions here. Right? So there should be 92 of them. We could print, again, we could have a solution count if we wanted to do those sorts of things here. But we get all of our solutions. So again, backtracking recursion. Right? We're going to try it and undo, try it and undo, try it and undo. Right? So I won't see you Thursday, but I'll see you Tuesday for lab. We'll do another chess puzzle. I like chess puzzles. I think they're lots of fun. It'll be the Knight's Tour, which is a little bit more complex, so I got to give you a little bit of help with that one. But it's a fun little puzzle. And then our next project will be on recursion. So we'll get lots of practice for this one, okay? All right, thanks, folks.